The foundations of science contain concepts that appear clear on the surface, but become uncertain when examined more deeply, and this keynote reveals how fragile our assumptions can be. At first glance, scientific ideas such as time, space, matter, cause, and even reality itself seem simple enough for anyone to understand. They are taught early in school, used in everyday conversation, and treated as if their meanings are fixed forever. Yet the moment scientists push beyond ordinary experience and begin investigating extreme conditions, whether at the tiniest scales of particles or the vastness of the cosmos, these familiar concepts start to lose their sharpness. What once felt solid becomes blurry, raising questions that force us to rethink what we thought we already knew. This uncertainty arises because science depends heavily on definitions, and definitions depend on human language. Language was developed for everyday life, not for describing the behavior of electrons, the curvature of spacetime, or the nature of consciousness. Words that seem precise in normal situations become stretched, awkward, or incomplete when applied to deeper levels of reality. For centuries, people assumed time flowed at a constant pace. Matter was made of tiny indivisible particles, and space was an empty stage on which events happened. These ideas were not wrong at the time. They were the best interpretations available based on observations and reasoning. But as new tools and experiments emerged, they revealed inconsistencies that exposed the hidden ambiguity buried inside these concepts. When scientists discovered that time does not move the same for everyone, or that particles do not have fixed positions until they are measured, the old definitions could no longer hold. The ambiguity was always there. It was just invisible until evidence demanded a revision. This shows that scientific knowledge is not a structure built once and left unchanged. It is a living system that grows, adapts, and transforms when new discoveries challenge the old framework. What makes the foundations ambiguous is not that science is unreliable, but that nature is far more complex than the early thinkers could have imagined. The more deeply we probe into the universe, the more we realize that our starting concepts may be too simple, too limited, or too tied to human intuition. Ambiguity becomes a sign that our understanding is incomplete, pushing scientists to refine theories, update models, and sometimes replace entire worldviews. Instead of ignoring uncertainty, science uses it as a guide, pointing toward areas where new breakthroughs may arise. These ambiguous foundations are not weaknesses. They are reminders that all knowledge begins with questions, and that every answer must remain open to improvement. Through this ongoing cycle of inquiry and revision, science continues to move closer to truths that better reflect the incredible complexity of the world we are trying to understand. Ambiguous scientific ideas often appear when language struggles to describe complex realities, and this keynote highlights the deep tension between human expression and the nature of the universe. Language is one of the most powerful tools we possess, shaping how we think, communicate, and build knowledge. But it was created to capture everyday experiences such as movement, heat, sound, or emotion. When scientists attempt to describe realms that lie far beyond the ordinary, like quantum behavior, the structure of spacetime, or the origin of life, our familiar words begin to stretch beyond their limits. This is where ambiguity begins, not because the ideas are meaningless, but because the language we rely on was never designed to handle such intricate details of reality. Take the word particle. In daily life, a particle is imagined as a tiny solid object. But in modern physics, a particle can behave like a wave, can exist in multiple states at once, and can be more of a probability than a physical object. The word no longer matches the behavior it is meant to describe. Similarly, the term time suggests a simple, consistent flow from past to future. Yet relativity shows that time bends, stretches, and changes depending on gravity and speed. Our vocabulary was not built for such elastic behavior, so it becomes ambiguous when used in scientific discussions. Another example is the concept of life. People use the word confidently, but in biology, defining life precisely is surprisingly difficult. Viruses challenge our definitions, synthetic cells blur boundaries, and new discoveries force scientists to constantly revise what counts as living. The same applies to species, intelligence, and consciousness, words that sound straightforward but collapse into gray areas when examined deeply. This is not a failure of science. It is a mismatch between the complexity of nature and the simplicity of language. When language reaches its limits, scientists often create new terms, redefine old ones, or rely on mathematical descriptions that bypass ordinary speech. Mathematics can express relationships and behaviors with far more precision than words, but it does not eliminate ambiguity entirely, because interpretation still depends on human understanding. Even in mathematics, symbols can be misunderstood or used differently depending on context. This shows that communication is always layered with uncertainty whenever ideas are complex. Ambiguity also arises because scientists themselves carry assumptions shaped by culture, intuition, and personal interpretation. When they use language to communicate their findings, the words can carry unintended meanings or oversimplifications. As a result, the scientific community continuously revisits definitions to ensure they match the latest evidence. This keynote demonstrates that ambiguous concepts are often a natural consequence of trying to express deep truths using tools that evolved for simpler tasks. Instead of treating this as a problem, science recognizes ambiguity as a signal that more precise language or improved models are needed. It is through this ongoing struggle between expression and understanding that science advances, slowly refining both the concepts and the words we use to describe the world. Revising foundational concepts is essential for scientific progress because knowledge is never static, and every generation discovers something that challenges what came before. When scientists begin to notice contradictions, unexplained results, or strange behavior in experiments, it signals that the current framework is no longer enough to describe reality accurately. If the foundational ideas remain unchanged despite new evidence, science would become rigid, unable to grow or correct itself. Progress happens only when researchers are willing to step back, question their assumptions, and redefine the very concepts they started with. This revision process has happened repeatedly throughout history. Early scientists believed the Earth was the center of the universe because it fit their observations and cultural expectations. But when astronomical measurements improved, the geocentric model failed to explain planetary motion. Revising the foundational idea led to the heliocentric model, which opened the door to modern astronomy. The same pattern appears in physics, where the concept of absolute time and space dominated for centuries until relativity showed that these ideas needed to be replaced with a more flexible understanding of spacetime. Without revising these basic concepts, many modern technologies and scientific insights would never have emerged. Revising foundations is not about admitting that old theories were useless. It is about recognizing that they were stepping stones. Every scientific model is an approximation of the truth, built to match the best evidence available at the time. As instruments, experiments, and methods improve, those approximations need refinement. This is how Newton's laws, though still incredibly useful, were expanded by Einstein's relativity and further extended by quantum mechanics. Each revision made the scientific picture more complete. Another important reason for revising foundations is that nature often behaves in ways that do not match human intuition. Ideas that feel obvious, like linear causality, fixed identities, or stable categories, begin to fail when studying atoms, ecosystems, or the cosmos. If science were limited to intuition, it would remain stuck. Revising concepts allows scientists to escape the boundaries of common sense and explore possibilities that seemed unthinkable before. Ultimately, progress depends on the courage to rethink what seems certain. Foundational concepts are not sacred, they are tools, and tools must evolve as the problems become more complex. By revising the base of knowledge, science sharpens its accuracy, broadens its reach, and moves closer to understanding the rich and intricate reality that lies beyond first impressions. Many breakthroughs occur when scientists question long-standing assumptions, because true discovery often begins where certainty ends. Assumptions act like silent rules that guide how people think, what questions they ask, and what explanations they consider possible. For a long time, these assumptions can seem completely natural, as if they are simply the way the world works. But when scientists dare to challenge them, they open the door to ideas that were previously hidden or unimaginable, and make uncomfortable, yet it is one of the most powerful engines of scientific progress. History shows that transformative advances rarely happen by following established paths. Instead, they emerge when someone refuses to accept a traditional belief without deeper investigation. When the assumption that diseases were caused by bad air dominated medicine, no one thought to look for microscopic organisms. Yet once this assumption was challenged, germ theory was born, changing medicine, sanitation, and public health forever. The same happened in physics when the idea of a fixed, unchanging universe was questioned. This shift eventually led to the discovery that the universe is expanding, reshaping our understanding of cosmic origins and evolution. Challenging assumptions also reveals the biases and limitations built into older models. Many early scientific frameworks were designed with limited tools and incomplete information. As technology improves, new data often contradicts old expectations, forcing scientists to ask whether their starting beliefs were too narrow. The assumption that matter behaves predictably, for example, collapsed when quantum experiments showed randomness and duality at the smallest scales. This realization opened the path to quantum mechanics, one of the most successful theories in science, powering everything from lasers to modern electronics. Sometimes assumptions limit imagination more than evidence. People once assumed heavier objects fall faster, not because experiments proved it, but because it fit intuition. Only when this idea was tested did gravity reveal its true behavior. This shows that questioning assumptions does not always require advanced tools. Sometimes curiosity and careful observation are enough to spark change. The greatest discoveries often begin with a simple thought: what if we're wrong? This question encourages scientists to look where no one has looked, test what no one has tested, and connect ideas in ways no one has attempted before. When assumptions are challenged, possibilities expand, new theories emerge, new technologies develop, and humanity gains a clearer view of the world. By refusing to accept limits imposed by tradition, science continues to grow, evolve, and uncover deeper truths about the universe. Ambiguity is not a weakness in science. It is a signal that deeper truths remain undiscovered, and this idea reshapes how we think about uncertainty. When people first encounter ambiguous results or confusing data, the instinct might be to see it as a flaw, something wrong with the theory, the experiment, or the understanding itself. But throughout scientific history, ambiguity has been the starting point of many major discoveries. It marks the boundary between what is known and what still waits to be explored. Instead of closing the door, ambiguity invites scientists to look more closely, to refine their tools, and to search for a clearer pattern hidden beneath the confusion. When early astronomers observed planets moving in irregular paths, the ambiguity did not mean the universe was chaotic. It meant that the old model was incomplete. The uncertainty led to the discovery of new laws of motion and a better understanding of gravity. The same pattern appeared in atomic physics. When electrons behaved in ways that classical physics could not explain, the ambiguity did not signal failure. It signaled the beginning of quantum mechanics, a field that eventually transformed technology and deepened our sense of how nature operates. Ambiguity also pushes scientists to question their assumptions. Sometimes the problem is not the data, but the frameworks used to interpret it. For example, the ambiguity in the nature of light, sometimes behaving like a particle, and sometimes as a wave, forced scientists to adopt entirely new perspectives. Instead of choosing one explanation over the other, they realized that reality might be more complex than simple categories allow. This led to wave-particle duality, a concept that reshaped both physics and philosophy. Another important aspect of ambiguity is that it prevents science from becoming stagnant. If everything appeared clear and complete, there would be no reason to investigate further. Ambiguous results challenge researchers to design better experiments, create new theories, and develop more precise language or mathematical descriptions. In this way, ambiguity fuels creativity and innovation, encouraging scientists to reach beyond the obvious. Perhaps the most valuable role of ambiguity is that it keeps humility at the center of scientific inquiry. It reminds us that even the most trusted ideas are still approximations, and that nature often holds surprises. Instead of treating ambiguity as a threat, the scientific mindset sees it as an invitation, a chance to uncover patterns that were previously invisible. Through this willingness to embrace uncertainty, science inches closer to deeper and more accurate truths about the universe. Modern physics, cosmology, and biology show that earlier definitions no longer fully match observed reality, and this has become increasingly clear as scientific tools have grown more advanced. Many ideas that once seemed solid were based on limited observations and the simplest explanations available at the time. As instruments improved and scientists gained the ability to measure smaller, larger, faster, and more complex phenomena, the universe revealed behaviors that no older definition could neatly contain. Concepts such as time, matter, energy, life, and even space itself began to stretch beyond traditional meanings. In physics, classical definitions assumed that objects had definite positions, time flowed uniformly, and forces acted in predictable ways. But quantum mechanics exposed a world where particles behave as probabilities rather than fixed objects, and where uncertainty is built into nature itself. Relativity then showed that space and time are not rigid backgrounds, but dynamic, flexible entities shaped by mass and motion. These discoveries did not simply extend old definitions. They showed the need for entirely new frameworks. Cosmology also challenged older ideas, revealing that the universe is not static but expanding, filled with mysterious components such as dark matter and dark energy. These phenomena do not fit into traditional definitions of matter or energy, yet they appear to shape most of the cosmos. Older definitions failed to predict or explain them, demonstrating that our understanding must evolve. Biology, too, faces shifting boundaries. Definitions of life struggle to include organisms like viruses or synthetic cells. Concepts such as species blur as genetics reveals unexpected connections and continuous evolutionary change. Even intelligence and consciousness resist clear definitions as new research expands what different forms of life can do. All these fields show that older definitions, while useful in their time, are no longer enough. The expanding complexity of scientific discovery demands new language, new theories, and new ways of understanding reality. Understanding and refining ambiguous concepts leads to sharper theories and more reliable knowledge, because clarity in science is something that must be earned, not assumed. When a concept is vague or loosely defined, it can guide thinking only to a limited extent. Scientists might use the same word but mean different things, or rely on an idea that fails to match what experiments reveal. This uncertainty becomes a barrier that prevents theories from describing nature with precision. By confronting ambiguity directly, scientists uncover hidden assumptions and replace them with clearer, more accurate definitions that strengthen the entire structure of understanding. As research progresses, new evidence often exposes gaps in old ideas. A concept that once worked well can become too simple for new observations. When scientists refine its meaning, they make it more capable of handling complexity. This process has been essential in fields like physics, where ideas such as energy, mass, and information had to be reinterpreted to fit discoveries at both cosmic and quantum scales. Each refinement removed confusion and opened the door to more accurate predictions. Clarity also helps different scientific fields communicate effectively. When ambiguous concepts are refined, researchers can build bridges between disciplines, connecting biology with chemistry or physics with information theory. These connections allow deeper insights and unified explanations of natural phenomena. At the same time, clearer concepts make it easier to design experiments, interpret results, and test theories in a consistent way. Refining ambiguous ideas strengthens science not by eliminating uncertainty, but by making sure that the uncertainty points in the right direction. When concepts become sharper, they guide researchers toward the questions that truly matter, helping them avoid misleading interpretations. Through this continuous process of clarification, science becomes more reliable, more predictive, and more capable of revealing the deeper truths hidden within the complexity of the universe.